The first Allied jet fighter to change the face of aviation, yet one that nearly fell victim to engines with a service life of just 10 hours. The British Gloster Meteor altered the rules of aerial combat. But did you know the engineering dramas and compromises its creators had to endure? Why did the first prototype take to the air powered by a competitor's engines rather than those of the project's originator? How did designers combat the severe buffeting that caused pilots to lose control at critical speeds? And why was the triumphant speed record of 1945 actually a clever marketing maneuver to save the factory? Today, we will examine the hidden defects and real test pilot reports of this aviation breakthrough. Watch the video to the end to discover the design secret hidden behind the tail of this pioneering jet. Frank Whittle filed a patent application in 1930. He was 23 years old. A pilot in the Royal Air Force, he had written a thesis on how flight could be achieved in a fundamentally different way, without pistons or propellers, relying purely on jet thrust. The Patent Office reviewed the application and granted the patent. Everything was official and documented. The British Air Ministry read the materials and concluded that it possessed no practical value. Whittle continued his work. He taught at a flying school, flew, and performed calculations. There was no money for research and no state funding. In 1935, the patent had to be renewed, which cost £5 sterling. Whittle could not find this sum, and the patent expired. The information became public, and in Germany, it was read very carefully. This is neither a theory nor an assumption. It is a documented fact that official British investigations confirmed after the Second World War. While Whittle was looking for £5, German engineers were working with his ideas in fully funded state laboratories. But history took an unexpected turn. In 1936, two of Whittle's former classmates from Cambridge University invested their own money and helped him found a small company called Powerjets. The staff consisted of just a few people, the budget was minimal, and the task was to build a working jet engine. By mid-1939, the engine was on the test stand and running. Its thrust was 270 kilograms. By modern standards, this is negligible. A small regional aircraft today produces dozens of times more thrust. But in 1939, it was the first jet engine in Great Britain that did not merely exist on paper, but actually rotated, produced thrust, and did not fall apart. The Air Ministry reviewed the materials again. This time, their attitude changed because the situation in Europe had changed. In September 1939, World War II began, and what had seemed like an academic experiment a year earlier suddenly took on a completely different meaning. Whittle received funding, finally. Concurrently, Gloster Aircraft entered the picture. Its chief designer, George Carter, met with Whittle and saw in his engine what officials had overlooked for 9 years. Not just an interesting technical concept, but the foundation for a fundamentally new aircraft. They agreed to work together. Carter sat down at the drawing board while Whittle continued refining the engine. The new machine received the company's internal designation, G-41. To the military, it was still just an experimental jet propulsion project, without a name, without guarantees, and without a certain future. But the wheels were already in motion. While Carter drafted and Whittle calculated, piston engine fighters were flying in the skies over Europe, pushing their engines to the absolute limit. Speeds were approaching 700 kilometers per hour, hitting a physical barrier. A piston engine with a propeller simply could go no further. Whittle had known this as early as 1930. It took 9 years and a world war for everyone else to realize it. George Carter faced a task for which there was no textbook. All the aircraft he had built before followed a single logic: engine in the front, tail in the back, wing in the middle. A piston engine turns a propeller, and the propeller pulls the aircraft forward. Everything was clear and proven over decades. The jet engine worked differently. It did not pull, it pushed. It drew air in from the front, compressed it, mixed it with fuel, ignited it, and expelled the hot gases out of the rear at tremendous speed. The reaction to this exhaust propelled the aircraft forward. It sounded simple, but housing such a machine inside an aircraft was an entirely different matter. Carter considered 3 options. The first was to place both engines in the fuselage, one behind the other. It was compact and aerodynamically clean. However, the air intakes would have to run through the entire nose of the aircraft, and the jet exhaust would exit directly beneath the tail assembly. This created serious control issues, as the hot gases would affect the control surfaces. The second option was engines under the fuselage in separate nacelles below. This was technically simpler, but an aircraft with two large protrusions beneath its belly would lose speed due to excessive drag. The third option was wing-mounted engines in separate nacelles on either side of the fuselage. Carter chose the third option. The main reason was practical. Wing-mounted engines were easy to access during maintenance. Technicians could open the nacelle and work comfortably without squeezing into the narrow internal compartments of the fuselage. For a combat aircraft that needed to be quickly prepared for its next flight, this was of immense importance. However, the wing-mounted configuration created its own problem. An engine is not simply a cylinder that can be bolted on. It passes directly through the structural framework of the wing, through the spars, the longitudinal beams carrying the entire load. Cutting a hole through them for the engine without weakening the structure was an engineering challenge no one before Carter had solved. He resolved it by mounting the engine to the front wing spar while letting it pass through the rear spar. A special banjo-style ring frame was integrated into the rear spar, a reinforced collar that supported the engine while maintaining the strength of the entire structure. The aircraft was designed modularly, using major subassemblies that could be built independently at different factories across the country and then mated together. This was a deliberate wartime decision, as production facilities were dispersed and bombings disrupted supply chains. If one factory stopped, the others could keep working. The nose section was a separate unit, housing the pressurized cockpit, armament, and nose landing gear. The cockpit canopy hinged to the side, not sliding backward like on most fighters of the era, but swinging sideways. The center fuselage was integrated into a single block with the center wing section and engine nacelles. Inside were the fuel tank and ammunition bays. The rear fuselage detached as a separate unit. Next was the armament. Originally, the design called for 6 20mm cannons, 4 mounted in pairs on either side of the cockpit and 2 more underneath it. The military looked at the lower pair and agreed to omit them. The location was highly impractical for servicing and reloading. This left 4 cannons, which was sufficient. The tail assembly deserves special attention. The horizontal stabilizer, the surface providing pitch stability, was raised unusually high, higher than on conventional aircraft of the day. The reason was simple. The exhaust jets from the engines were hot and fast. If the stabilizer were positioned directly in the path of these jets, the elevator would lose effectiveness. By raising the stabilizer, Carter moved it out of the path of the direct exhaust flow. This solution was later copied by dozens of designers worldwide. By the end of 1941, the blueprints were complete. The machine existed on paper in full detail. Only one thing remained: to find engines that would fit into it and not fail in the air. This, however, turned out to be far more complicated. In the early 1940s, a jet engine was not a commodity you could order from a catalog. It was an experiment, a living, unpredictable, and highly unreliable experiment. Once Carter completed the airframe designs, the project faced a practical question: which engine to install? Whittle's design was the obvious choice, but was it the only one? The Ministry of Aircraft Production decided not to put all its eggs in one basket. By that time, several organizations in Great Britain were developing jet engines. Each pursued its own path, and each believed its approach was the correct one. The first was Whittle's company, Power Jets. Its engine was designated the W.2B/23. It used a centrifugal compressor, meaning air was drawn into the center of a rotating impeller and thrown outward by centrifugal force into a ring of combustion chambers. The layout was simple, reliable, and straightforward. By 1942, Rolls-Royce acquired a license for this engine and brought its massive engineering staff to bear on its development. The results were immediate, yielding a significantly improved version designated the W.2B/23C. This was the engine manufactured by Rover Motor under the commercial name Welland, producing 771 kilograms of thrust. The second participant was the de Havilland Company. They developed an engine designated the H1, also featuring a centrifugal compressor. Its test stand thrust was 1,040 kilograms, noticeably higher than Whittle's design. On paper, it was the clear winner. However, The de Havilland engine had a design nuance that became a problem as soon as they tried to install it in Carter's airframe. The engine was wider. Not by much, but enough that it would not fit into the nacelle designed for Whittle's engine. This required redesigning the rear wing spar and the nacelle itself, delaying testing and adding several months of extra work for the designers. Nonetheless, it was the de Havilland H1 engine that was installed on the first flight prototype. This was not because it was better, but because it was ready for installation before the others. The third competitor was Metropolitan Vickers. They took a fundamentally different route, choosing an axial compressor instead of a centrifugal one. The difference is that in an axial compressor, air flows along the engine's axis, passing through several stages of blades that compress it step by step. This is more difficult to manufacture and requires more precise balancing, but the engine is longer and narrower, making it more streamlined. The Metropolitan Vickers engine was designated the F2, with a test stand thrust of about 1,000 kilograms. It was also installed on one of the prototypes and tested alongside the others. Testing ran from April to the end of 1943. All three variants flew, and all three were compared using the same parameters: thrust, reliability, fuel consumption, behavior across different operating regimes, and ease of maintenance. The Air Ministry gathered the results and made its decision. Whittle's engine, the W.2B/23, produced by Rolls-Royce, won. This was not because it was the most powerful. The de Havilland engine produced more thrust. Nor was it because it was the most advanced. The axial design of the Metropolitan Vickers was technically more intriguing. It won due to a combination of factors that, in wartime, were far more critical than theoretical perfection: reliability, maturity of design, the feasibility of rapid mass production, and ease of field maintenance. Behind the Rolls-Royce engine lay years of refinement, the company's vast manufacturing experience, and an extensive nationwide service network. This was what mattered. But the story of the engines does not end there. It was only entering its next phase. While the comparative tests were underway, Rolls-Royce engineers did not stand still. They continued to improve Whittle's basic design. The next step was the Derwent 1 engine with 900 kilograms of thrust, which was fitted to later production aircraft of the first variant. This was followed by the Derwent 5, producing 1,590 kilograms of thrust, double that of the original Whittle engine. Each new engine required the airframe to be reinforced. More thrust meant higher structural loads during maneuvers. Carter and his team revised the aircraft in parallel for each new generation of engines. It was an active, evolving process. The airframe and the engine grew together, pushing each other forward. By early 1943, everything was set for the next step. Blueprints were in production, the engine was on the stand, and the prototype was in the assembly shop. All that remained was to get the machine into the air. March 5, 1943, turned out to be an ordinary working day at the factory airfield in Gloucester. There were no ceremonial speeches and no official delegations. Just a few engineers, a few mechanics, and test pilot Michael Daunt in the cockpit of the prototype bearing the serial number DG206/G. The letter G at the end of the serial denoted special status. The aircraft was not to leave the factory grounds without security. It was too secret, too important. Daunt started the engines. The sound was unlike anything people at the airfield had ever heard. It was not the sharp crackle of a piston engine, nor the rhythmic rumble of a radial engine. It was a rising, high-pitched whine that grew steadier as the RPMs reached operating levels. It was almost metallic, a nearly pure tone. Mechanics standing nearby later recalled that there was something simultaneously unsettling and mesmerizing about the sound. Daunt opened the throttle and began his takeoff run. The aircraft accelerated down the runway and lifted off smoothly, without jerks or deviations. It climbed, performed several planned maneuvers, and tested handling characteristics at various speeds and engine settings. The first flight lasted about 17 minutes. Upon landing, Daunt climbed out of the cockpit and offered a brief technical comment. Handling was normal, the engines operated properly, and there were no complaints regarding the aircraft's behavior. A professional test pilot is not given to hyperbole. His job is to record facts, not to marvel. But the fact remained: the aircraft had flown. Testing continued through April and May. 2 more prototypes powered by Rolls-Royce W2B/23 engines joined the first, which had the de Havilland H1. The aircraft flew, data accumulated, and the design was refined. On July 20th, 1943, prototype DG-205/G took off with Rolls-Royce engines. On July 24th, the next one, DG-202/G, also with Rolls-Royce engines, made its flight. Over the next 2 months, all 3 aircraft flew intensively, while a fourth prototype, DG-204/G, powered by Metropolitan Vickers F2 engines, was tested concurrently. By this point, test pilots had accumulated enough impressions to speak about the machine in concrete terms. First, everyone noted the smoothness of operation. A piston engine vibrates. It is in its nature as pistons move up and down, creating constant pulsations. A jet engine rotates. There are no pistons and no pulsations. In the air, the aircraft was noticeably quieter and smoother than any piston fighter of the time. Second was the acceleration. In a piston engine fighter, acceleration was felt in surges, especially at low altitudes where the air is dense. The jet engine provided smooth, continuous acceleration. Pilots described it as the sensation of the aircraft simply sliding forward without meeting resistance. Third, and this proved crucial for understanding combat employment, at high speeds, handling deteriorated. Control stick forces increased, and the aircraft began to buffet. This was not a design flaw, but physics. At speeds piston aircraft had never approached, air behaved differently. The designers documented this and began thinking about how to resolve it. At the end of 1943, a mock dogfight was staged between the new Meteor F3 and one of the finest fighters of the era, the Hawker Tempest Mark V. The Tempest was an outstanding machine, one of the fastest piston engine fighters ever produced in Great Britain, with a top speed of about 700 kilometers per hour at sea level and an armament of 4 cannons. Experienced pilots respected it for its responsiveness and power-to-weight ratio. The engagement lasted several minutes. Upon landing, the Tempest pilot remarked simply, "The Meteor outperforms me in almost every parameter. I have nothing to counter it with at speeds above 600 kilometers per hour." This was not praise for the sake of empty words. It was the sober, professional conclusion of a man who realized that the era defining his entire flying career was drawing to a close. The Meteor surpassed the Tempest in top speed, climb rate, and high-altitude performance, where the piston engine lost power due to thin air, while the jet engine operated much more smoothly. At low speeds, however, the Tempest held its own better in maneuverability. Early jet engines responded poorly to sudden throttle inputs, causing the Meteor to lose out in tight, slow turns. This observation would later yield practical consequences. The first 20 production aircraft, the Meteor F1, left the factory in early 1944. They were powered by Rolls-Royce Welland engines, each producing 771 kilograms of thrust and armed with 4 20mm cannons. The top speed was 676 kilometers per hour. The aircraft was ready for service, and service would not wait, for it was at this very moment that an adversary appeared over England whom no existing interceptor could easily manage. In the summer of 1944, a new enemy appeared over southern England. It was unpiloted, did not maneuver, and made no evasive action. It simply flew low, fast, and in a straight line, accompanied by the distinctive rasping rattle of a pulse jet engine, a sound London residents quickly learned to recognize and fear. This was the V-1, the German flying bomb, which modern classification would define as a cruise missile. It was about 8 meters long with a wingspan of 5.5 meters, carrying an 850-kilogram warhead of high explosives. Its flight speed ranged from 600 to approximately 650 kilometers per hour at operational altitude. And that final figure was where the entire problem lay. Piston engine fighters of the period could technically achieve such speeds, but only in a dive, sacrificing altitude. In level flight, catching a V-1 was extremely difficult. By the time an interceptor accelerated to the necessary speed, the target had pulled ahead. By the time it assumed a favorable firing position, precious time had slipped away. The first and only squadron to receive the new Meteor F-1 was number 616 Squadron of the Royal Air Force. In the summer of 1944, they began converting to the new aircraft. The mission was straightforward: intercept the V-1. On paper, the Meteor was better suited for this than any other British aircraft. Its jet engines did not lose performance at high speeds the way piston engines did, and acceleration was smooth and predictable. but practice proved more complex than theory. Early sorties showed that catching a V-1 was possible only if everything went to plan. If the interceptor was guided onto the correct vector by ground controllers in advance, if altitude and speed were correctly calculated, and if the target flew exactly where anticipated. Yet the V-1 possessed one characteristic that was initially underestimated. Shooting it down was dangerous. An 850-kilogram explosive payload was not just a target to destroy. It was an object that, if detonated in close proximity to the interceptor, could destroy the interceptor as well. Firing distances had to be precisely judged, close enough to score hits, yet far enough to survive the resulting blast. Pilots gained this experience on live sorties. On August 4, 1944, a No. 616 squadron pilot spotted a V-1 ahead and below his aircraft. He eased the Meteor into a shallow dive, building speed. The gap closed. He established his firing position and squeezed the trigger. The cannons fired a brief burst, then fell silent. Gun jam. At the most critical moment, with the target directly ahead. For a few seconds, the pilot assessed the situation. The V-1 kept flying, with London only minutes away. He then made a decision written in no manual. He positioned his Meteor right alongside the V-1, so close that his wingtip was practically touching the wing of the flying bomb. Without making contact, just flying side by side. Then, he banked his fighter sharply. When an aircraft wing abruptly changes attitude at high speed, it generates a powerful disturbance in the airflow, a pressure wave that radiates outward. The V-1's gyroscopic autopilot was configured to compensate for smooth variations in airflow. It could not handle a sudden, localized disruption right at its wingtip. The V-1 rolled, lost stability, and plunged to the ground in an uninhabited area short of its target. The first victory was achieved without firing a single shot. This technique, tipping the flying bomb using the aerodynamic vortex of the wing, became known among No. 616 squadron pilots as a viable method in case of weapons failure. It demanded precise judgment of distance and cool nerves. Too close, and the pilot might not escape the blast if the bomb detonated. Too far, and the disturbance of the airflow would be insufficient. By the end of the summer of 1944, Meteors had destroyed 13 V-1s. 13 was a small fraction compared to the total intercepts performed by piston engine fighters and anti-aircraft artillery. But for a squadron transitioning to a fundamentally new technology, it was a tangible combat result. Furthermore, there was another effect that could not be measured in numbers. British commands skillfully utilized the sheer existence of a jet fighter. Reports about the new aircraft were carefully released to the press, enough to boost public morale and show that the nation was advancing technologically, but not enough to reveal the machine's true performance. It was a propaganda asset used deliberately. But the true test for the Meteor lay ahead, not over England, but over the continent. And there, an adversary of an entirely different nature awaited. On January 20th, 1945, the first Meteor F.3 variants flew to the continent. The squadron deployed to Belgium. Their official mission was to provide air defense for liberated territories. Their unofficial mission, written cautiously between the lines in official documents, was to locate and engage German jet fighters. By then, enough was known about the Messerschmitt Me-262 to treat it seriously. Powered by two axial compressor engines producing roughly 800 kilograms of thrust each, it had a top speed of about 850 kilometers per hour and carried four 30mm cannons in the nose. The aircraft had entered frontline service in mid-1944 and had already proved itself in engagements with Allied bombers. It was a class apart from piston fighters, and British command understood that an encounter between two jet aircraft in the air would be more than a simple dogfight. It would be a technological test analyzed for years to come. In March 1945, all of No. 616 Squadron was redeployed from Belgium to the Netherlands. The patrol sector changed, and sorties became more frequent. And here begins a chapter of history that remains without a definitive documentary explanation to this day. Throughout their entire deployment on the continent, from January to May 1945, pilots of No. 616 Squadron never once engaged a Messerschmitt Me-262 in aerial combat. There was not a single confirmed clash, none shot down, and none damaged in combat with a jet-powered opponent. This seems strange. Both aircraft flew over the same theater of operations, operated in the same altitude ranges, and carried out patrol and reconnaissance sorties. Logically, an encounter should have occurred, yet it never did. Post-war historians have proposed several theories. The first is operational. By early 1945, the German jet fleet suffered from an acute fuel shortage. Aviation fuel production was collapsing under Allied bombing campaigns against refineries. The Me-262s flew far less frequently than they technically could, conserving their engine life and fuel for priority missions, primarily the interception of heavy bombers, which were inflicting the greatest damage on German industry. A British jet fighter was low on this list of priorities. The second theory is tactical. British command deliberately restricted Meteor patrol areas, preventing them from flying deep into enemy-held territory. The official reason was to prevent the capture of secret technology. A jet forced to land on the German side could yield valuable technical intelligence. This concern was real and documented. Direct orders existed limiting Meteor operations over German-controlled territory. The third theory is the most intriguing. British archives contain accounts from several pilots who reported visual contact with enemy jets. The silhouette was visible, and the distance was sufficient for identification, but none of these encounters escalated into combat. Pilots described it differently. One wrote in his report that the German pilot, judging by his maneuver, had also spotted him and simply turned away. He did not attack, nor did he dive or climb away. He simply altered course and vanished into the haze. Why he did not attack remains unknown. Perhaps the German pilot was ordered not to engage single fighters, conserving fuel and engine life. Perhaps he assessed the situation and deemed it unfavorable, or perhaps there was another reason. No surviving German documents offer a direct answer, or at least none have yet been integrated into historical research. On April 13, 1945, the Meteors flew their first official offensive combat mission over Europe, targeting ground installations. This represented a shift in role, from interception and patrol to ground attack. The jet aircraft proved effective in this capacity as well. But the main event, a clash of two jet fighters in aerial combat, never transpired. Aviation historians still refer to this as one of the most curious non-events of World War II. Two aircraft, each opening a new page in aviation history, never wrote it together. They parted ways in history. The Messerschmitt Me-262 ended its journey with the close of World War II, while the Meteor flew on towards something unexpected, not combat and not patrol, but a race. May 1945. The Second World War in Europe had ended. Gloster aircraft sat with an established production line, a proven design, and a pressing question: what next? Wartime contracts were wrapping up. The Royal Air Force had received its planes, but peacetime requirements were vastly different. Fewer aircraft, less urgency, and greater demands for cost efficiency. New orders were not guaranteed. Company management took a sober look at the situation. The Meteor was a solid aircraft, perhaps the best jet fighter available on the open market in 1945. But to sell these planes to other nations, they first had to convince them that they wanted the Meteor, and for that, they needed publicity. In 1945 aviation, publicity took its most convincing form: a world speed record. The idea was simple and elegant. Take a production aircraft, prepare it specifically for a record run, and set an absolute world speed record. After that, any potential buyer would view the Meteor in a different light. Preparations began immediately after the end of hostilities. For the record flight, they selected a Meteor F4, the latest variant at the time, equipped with Rolls-Royce Derwent 5 engines producing 1,590 kilograms of thrust each. Compared to the early production Meteor F1, thrust had more than doubled. Now, to what they did to the aircraft before the attempt. They stripped away all armament, 4 cannons, ammunition, and all equipment associated with the fire control system. These were not minor items. It relieved the aircraft of some 300 kilograms of weight. They removed all equipment unnecessary for a single specific flight. The radio was reduced to a minimum, and only essential navigation instruments remained. The airframe surfaces were polished, literally hand-polished to a mirror finish. Every scratch or imperfection on the skin generates microturbulence, which contributes to overall drag. At cruise speeds, this is imperceptible, but at speeds exceeding 800 kilometers per hour, it is highly significant. All panel joints were sealed with special tape. When preparations were complete, The aircraft was no longer a fighter in the strict sense. It was a high-speed machine optimized for a single task: to fly a measured course as fast as possible. On November 7, 1945, at Herne Bay on the southern coast of England, the specially prepared Meteor F-4 took to the skies. The world speed record at the time belonged to a German piston-engine fighter, the Messerschmitt Me-209, at 755 kilometers per hour. It had been established back in 1939 and had held throughout the Second World War. The Meteor completed the measured course at a speed of 969.6 kilometers per hour. This was 214 kilometers per hour faster than the previous record. Not just a new record, but a different order of magnitude. Aviation had stepped into a new dimension of speed right before everyone's eyes. The press reacted precisely as Gloster had hoped. Headlines appeared the next day in all major publications, and photos of the aircraft circulated worldwide. And the contracts began to arrive. Argentina became the first nation to purchase the Meteor F-4, followed by Denmark, Egypt, Belgium, and the Netherlands. Later, they were joined by Australia, Israel, Brazil, Ecuador, and several other states. In total, 1,010 Meteor F-4 aircraft were produced. A single record-breaking flight had opened up the export market for an entire aircraft program. This was neither an accident nor luck. It was a deliberate marketing calculation executed with a precision any modern sales department would envy. Gloster understood a simple truth. In the aviation of that era, reputation was built not on promotional brochures or specification tables, but on concrete proof. A world speed record was the most absolute proof possible. Yet the record had been set by a specially lightened machine. A standard production aircraft with full armament and operational equipment flew slower. The designer's next task was to bring the production aircraft as close as possible to the performance demonstrated by the record breaker. Work on the next, most advanced version of the Meteor was already well underway. When engineers sit down to design a new version of an already flying aircraft, they possess something unavailable during the creation of the first prototype: real operational experience. Not calculations, not wind tunnel tests, but the first-hand observations of live pilots who flew the machine in real-world conditions and knew exactly what hindered them, what was lacking, and what could be improved. By 1947, Gloster's designers had accumulated plenty of this experience. The base for the new version was the Meteor F-4, a capable machine, but one with a series of limitations that became increasingly obvious as speeds rose and combat requirements evolved. The first thing pilots pointed out was stability at high speeds. When accelerating past a certain threshold, the Meteor F-4 began to behave nervously. Slight disturbances in the airflow caused yawing, spontaneous swinging of the nose left and right. It was not critical, but it was unpleasant and tiring on long flights. The cause lay in the tail unit. Its geometry, selected during the design of the early prototypes, did not function optimally at high speeds. The designers altered the shape of the vertical stabilizer, the fin, making it taller, and revised the geometry of the horizontal stabilizer. These changes were not radical but precise, akin to adjusting a fine tool to fit a specific hand. The second change concerned the fuselage. The rear fuselage of the Meteor F-4 was slightly too short relative to its overall layout. This affected its moment characteristics, how the aircraft reacted to control surface deflections. The fuselage was lengthened, not by much, but enough to improve the aircraft's balance. Third was the fuel. The range of the Meteor F-4 without external drop tanks was adequate for an interceptor, but modest for an aircraft expected to perform a broad range of missions. In the new version, an additional fuel tank was integrated inside the fuselage. The fourth change was the cockpit canopy. On previous versions, the canopy featured a framed construction with metal ribs between the glass panels. Each rib represented a blind spot for the pilot. In aerial combat, visibility to the rear and sides is critical. The new canopy was made bubble-shaped, formed from a single piece of transparent material without any framing. Cockpit visibility improved dramatically. Fifth, and this warrants special mention, the Meteor F-8 became the first production British fighter in history to be fitted with an ejection seat. Until then, emergency escape from a jet fighter had been a severe hazard. In piston aircraft, a pilot could simply roll over the side of the cockpit as speeds permitted it. In a jet, speeds were entirely different. Attempting to bail out in the conventional manner at speeds above 400 to 500 kilometers per hour meant the airflow would literally pin the pilot to the airframe or hurl him into the tail assembly. The ejection seat resolved this issue decisively. A cartridge charge propelled the pilot and seat upward with enough acceleration to clear the airflow around the aircraft. A parachute then deployed. In 1948, this was not a standard feature. It was a fundamental shift in combat aviation safety philosophy. The engines on the new variant were also updated. In place of the Derwent 5, they installed the Derwent 8, with thrust rising from 1,590 to 1,633 kilograms per engine. Though a modest increase in percentage terms, the engine was significantly more reliable and operated more smoothly during transient states, when fuel flow was adjusted rapidly. The gun sight became gyroscopic. A standard reflector sight showed a static aiming point with parallax correction. The gyro gun sight, however, accounted for the angular velocity of the target and automatically calculated lead angle. Simply put, it calculated where to shoot while the target was in motion. The pilot only had to keep the target in the reticle while the electronics handled the correction. Combat capabilities were expanded via underwing stores. Instead of drop tanks, 454 kilogram bombs could be carried, one under each wing panel, or up to 16 76mm unguided rockets on launch rails under the wings. This transformed the Interceptor into a versatile combat machine. The first flight of the Meteor F-8 took place on October 12, 1948. Its maximum speed was 960 kilometers per hour, service ceiling was 13,100 meters, and range without external fuel tanks was 965 kilometers. A total of 1,183 aircraft of this modification were produced, more than any other version of the Meteor. It was a mature machine, not experimental or record-breaking, but a workhorse, an aircraft that did everything required of it and did so reliably. It was this version that was sent to where one of the most intense aerial conflicts of the post-war decade would soon erupt. In February 1951, 14 Meteor F-8s and 4 Meteor T-7 trainers arrived at an airbase in Japan. They were assigned to No. 77 Squadron of the Royal Australian Air Force, operating under the United Nations Command in Korea. The pilots began transitioning to the new equipment. Most of them had previously flown piston-engine aircraft. By then, the Korean War had been underway for 8 months. Airspace over the peninsula was divided unofficially, but very clearly. In the northern sector lay the zone Allied pilots called MiG Alley, dominated by the Soviet-built MiG-15 jet fighter. On July 29, 1951, the Australian Meteors flew their first combat mission. They patrolled the airspace in the Cheongju area alongside North American F-86 Sabre fighters. No enemy appeared in the air. The following weeks were similar: patrols, ground cover, and escort duties. Flight experience under Korean theater conditions gradually accumulated, involving weather, terrain, and navigation specifics. On August 29, 1951, an 8-plane flight of Meteors was tasked with escorting Boeing B-29 heavy bombers to the Yalu River area, the border between Korea and China, and the northern limit of their operational zone. At an altitude of 10,668 meters over Cheongju, the formation was jumped by 6 MiG-15s. The engagement was brief. 2 Meteors were damaged, and 1 was shot down. This first clash immediately revealed the core reality. The MiG-15 was faster than the Meteor at high altitudes and possessed a superior rate of climb. The Soviet fighter featured swept wings, a design choice that significantly reduced drag at high speeds. The Meteor had a straight wing, which was optimal for speeds up to 900 kilometers per hour, but fell short against a swept wing at higher velocities. Cruising altitude differences also mattered. The MiG-15 preferred to operate at heights of 10,000 to 15,000 meters, where the thin air gave it a speed advantage. The Meteor was more effective at medium altitudes, from 5,000 to 8,000 meters. The enemy's tactics were well drilled: climb well above the patrolling Meteors, choose the moment, and dive at high speed. After 1 or 2 passes, they would zoom climb back to altitude, where the Meteor could not effectively pursue them. On December 1, 1951, an engagement occurred that became the costliest for the Australian squadron. 12 Meteors were patrolling at an altitude of 5,800 meters. The enemy was spotted just as the MiGs began their attack, diving from 15,240 meters. The altitude difference was nearly 10 kilometers. The Australians did not dive away. They accepted battle at their own altitude, where the Meteor's maneuverability was better. In a high-speed dive, the MiG-15 held the advantage, but in level turns at medium altitudes, the performance gap narrowed. On the first pass, the MiGs downed one Meteor, and the dogfight dissolved into individual pairings. During this engagement, Meteor pilot Bruce Gogerly managed to bracket a MiG-15 in his gun sight. From a range of 360 meters, he fired a long burst from his 4 cannons and shot it down. This was the Meteor's first confirmed victory over an enemy jet fighter. Yet the outcome of the battle was severe. 4 Meteors were lost, and only 1 MiG-15 was destroyed. Following this battle, Command received a report from the squadron's pilots. It contained a clear assessment of the situation. As an air-to-air fighter against the MiG-15 at high altitudes, the Meteor was at a disadvantage. This was not due to poor piloting or weak armament, but because of objective structural differences between straight and swept wings. It was a candid professional document. Command made a decision that looked like a retreat at first glance, but was in fact a sensible tactical choice. The Meteors were reassigned to the ground attack role. On January 8, 1952, 4 Meteor F-8s, armed with 8 unguided rockets and full cannon ammunition, struck a ground target in Chongjin. The raid went to plan, opening a new chapter in the aircraft's operational history. In January 1952, the squadron flew 769 ground attack sorties. In February, operational tempo rose to 1,000 sorties a month. At low and medium altitudes, the Meteor performed confidently as a ground attack aircraft. 4 cannons and underwing rockets provided substantial firepower, and its speed allowed quick egress from ground fire. The reliability of the Derwent engines had been thoroughly established by that stage. In total, 90 Gloster Meteor F-8s participated in the Korean War. Korea gave the Meteor a candid and demanding assessment, not a condemnation, but an appraisal. The aircraft had been created at the end of World War II to meet the needs of that era. The MiG-15 appeared later, designed with accumulated jet experience, including captured German research on swept wings. Comparing them is like comparing the first generation of any technology with the second. But how the Australian pilots flew this machine in real combat conditions is a separate story of professionalism that stands independent of the aircraft's performance figures. The Meteor survived Korea and continued its service. After Korea, the Meteor did not retire. It was not an aircraft that bowed out quietly. While the fighting continued in Korea, an entirely different version of the machine, a night fighter, had already been flying in Great Britain for several years. The story of its origin is revealing. In January 1947, the Air Ministry formulated requirements for a 2-seat jet night fighter. The mission was to counter massed night bomber raids at altitudes between 7,500 and 9,000 meters. The aircraft had to acquire targets in the dark independently, using an airborne radar set. Developing an entirely new machine required time, so Gloster proposed a faster solution. Take the existing 2-seat Meteor T-7 trainer and convert it into a night fighter by installing a radar set inside an elongated nose section. The proposal was accepted, and refinement and production were handled by Armstrong Whitworth, which already possessed experience producing other Meteor variants. On May 31, 1950, the first Meteor NF-11 night fighter took to the air. Structurally, it was a heavily revised aircraft. The wingspan was increased to 13.1 meters, returning to dimensions close to the original F-1 variant. The 4 cannons were moved from the nose to the wing panels, freeing up the nose for the radar installation. The cockpit was made into a pressurized tandem 2-seat configuration, accommodating a radar operator alongside the pilot. The power plant was retained from the Meteor F-8, Rolls-Royce Derwent 8 engines. Subsequent variants including the NF-12, NF-13, and NF-14 were produced, featuring radio compasses, cockpit air conditioning, enlarged air intakes, and different radar units. In total, 358 night fighters of various modifications were manufactured. In 1956, the Meteor appeared on 3 sides of a single conflict during the Suez Crisis. Egypt nationalized the Suez Canal, and Great Britain, France, and Israel conducted a joint military operation. British Meteors in the night fighter configuration operated with the RAF. Israeli Meteor F-8s covered ground operations. Egyptian Meteor F-4S, purchased several years prior, stood on the opposing side. One aircraft, three nations, one conflict. It was no longer a story about cutting-edge technology, but rather about how machinery disperses across the globe and lives a life of its own, independent of the intentions of those who created it. During those same years, the Royal Air Force used meteors in localized conflicts in Kenya, Aden, Malaya, and Cyprus. The French Air Force deployed them in Algeria. In all these theaters, they operated primarily as ground attack aircraft supporting ground forces. By the late 1950s, frontline RAF units began replacing the Meteor with more modern designs. In 1961, the last Meteors were withdrawn from active combat service in British aviation. Yet elsewhere in the world, the story continued. In Brazil and Ecuador, Meteors remained in service until the early 1970s. 25 years of active service, from the first production machines of 1944 to the beginning of the next decade, was a remarkable span for an aircraft built under strict wartime conditions from whatever was available. What remains of the Meteor? More than just museum pieces, though many exist, at the Royal Air Force Museum Cosford, the Imperial War Museum in Australia, and in several private collections worldwide. Something more critical remains. The Meteor was the first in a whole series of developments that later became industry standards. It was the first Allied jet fighter to fly and participate in active combat operations. It was the first aircraft to set a post-war world speed record, opening the era of speeds above 900 kilometers per hour for production aviation. It was the first British production fighter with an ejection seat. It was Great Britain's first export jet aircraft. None of these milestones is merely a formal line on a list. Each of them changed something concrete about how aircraft were subsequently built and operated. Ejection seats became standard across all jet aviation, as did modular airframe assembly from large independent subassemblies, and placing engines in wing nacelles to ensure convenient maintenance access. These are not exaggerations, they are simple facts about how one machine influenced those that followed. Frank Whittle filed a patent in 1930 for an engine the military deemed useless. George Carter took that engine in 1940 and built an aircraft around it. In 1944, No. 616 squadron pilots took to the sky in it and intercepted the first cruise missile in British aviation history, without firing a shot, using only the aerodynamic vortex from a wingtip. Australian pilots in Korea in 1951 evaluated the machine's capabilities with professional honesty, endured difficult combats, and found the correct application for it. And somewhere in Brazil or Ecuador, in the early 1970s, the last active-duty Meteor completed its final scheduled flight. It taxied to its parking space, and the engines shut down. There were no ceremonial speeches, and no photos on the front pages. The aircraft simply finished its work. That is precisely how truly reliable machines end their journey. Not with a bang, but with silence, and with the sense that everything required of them had been accomplished.